Hi everyone. In this section we will consider connected objects. In order to do this, we're going to have to make use of Newton's third law. Newton's third law is the law of action-reaction. It says that when an object exerts a force on a second object, the second object exerts an equal in magnitude but opposite in direction force back on the first. So this is a very specific definition of Newton's third law. You might have heard it loosely stated before as for every action there's an equal and opposite reaction. That's where this comes from, but Newton's third law refers specifically to the interaction of forces between two objects. Every single force is caused by one object on another. It's an interaction between two objects, and that force acts on both objects. So there's an action force on one object and a reaction force on the other. And these two forces are called action-reaction pairs. When we're identifying action-reaction pairs, we need to keep in mind that these forces act on different objects. If a force is due to an interaction between two objects, one force acts on one object and the other acts on the second object. Secondly, they are equal in magnitude and they're opposite in direction. It will be important to identify action-reaction pairs when using connected objects because that will allow us to link the force information between different objects and to solve the problem. Let's look at some examples of identifying action-reaction pairs, and then we'll see how to apply this to numerical problems. Example 20, consider a person pushing a box across a horizontal frictionless surface. Draw free body diagrams for the person and the box and identify the reaction force to all action forces that are present. All right, so I've drawn a box here for each of the person and the box to start the free body diagram. We can start by adding the weight of the object for each one, so Fg of the box and Fg of the person. Then we'll have a normal force because they're on a surface, so the normal force on the box and the normal force on the person. The person pushes on the box, so there's going to be a force here. I'm going to call it F and write person on box. Now already, because of Newton's third law, I know that there's a reaction force. So when a person pushes on a box, the reaction is that the box actually pushes back on the person with the same force. So let's add that F of the box on the person. Now there's one more force. This person is walking and pushing on the box. So there's a forward force from the person walking. So I'll call that F walk there. There's no friction, so those are all the forces that we have. So let's talk about their reaction forces. So first let's start with the normal forces. The normal forces are due to the surface, the floor, pushing up on the box or pushing up on the person. So the reaction to the normal force is that the person pushes down on the floor, or the box pushes down on the floor. That's the reaction force. So if we just talk about the box, the floor pushes up on the box to create this normal force, so then the reaction has to act on the floor. It always has to be on the other object that's causing the force. Gravity is interesting, so then we have gravity acting on each object. Gravity is due to the attraction force of the mass of the Earth, which is pulling down on the object, so pulling down on the person in this case. So the reaction has to act on the Earth, and the reaction is that the person pulls up on the Earth. And same for the box. The force of gravity pulls down on the box. The reaction is that the box this time, actually pulls up on the Earth. So you may be wondering, if that's true, why doesn't the Earth experience a force from all of the people and buildings and objects on its surface? Well, it does. Newton's third law says that it does experience the same force, but because of Newton's second law, which is F net equals ma, we know that acceleration is proportional to 1 over m when the force is constant. So the Earth is so massive that the same force causes a very tiny, almost negligible acceleration on the Earth. Okay, and then we have this reaction and interaction forces that we already talked about. The person pushes on the box, and then the box pushes back on the person. This walking force is due to the person, so what happens is the person pushes backwards on the earth. This is how we walk. So they'll push. We actually do need friction to do this, so we would need friction to walk, but how it works is we push down and back on the earth, and then the earth will push up and forwards on us, allowing us to walk. Example 21, a small car is involved in a head-on collision with a large truck on the highway. Which vehicle experiences the greater force? Which vehicle experiences the greater acceleration? All right, so it looks something like this. Newton's third law tells us that they both experience the same force. So the car exerts a force on the truck, and the reaction is that the truck exerts a force on the car. It doesn't matter which one you call the action and which you call the reaction. So they're the same, but which one experiences the greater acceleration? As I just showed, due to Newton's second law, we have acceleration proportional to 1 over mass, so inversely proportional to mass. So this means that the larger mass of object, which is the truck in this case, would experience the lower acceleration. So the car has the greater acceleration, assuming that it's less massive than the truck. So this is assuming that the mass of the car is less than the mass of the truck, which means that its acceleration is greater. Example 22, consider a 12 kilogram box and a 10 kilogram box that are connected via a rope. A 40 Newton applied force is directed horizontally onto the 10 kilogram box. What is the acceleration of the boxes if the surface is frictionless? All right, so it's going to look something like this. We have a 10 kilogram box here, let's call box 1, and then a 12 kilogram box, which we'll call box 2, and there's an applied force of 40 newtons on box 1. There's a rope connecting these two boxes, and they're on a frictionless surface. Okay, so we have a normal force on each box, Fn1, Fn2, the weight of each box, and then we have tension. So in a rope, the tension will be the same on both sides. And we know that also because of Newton's third law. So these are the interaction forces here. We have the force of box 1 pulling on box 2, which is this tension force, and the force of box 2 pulling on box 1, which is this tension force. So they're equal and opposite in direction. And now we want to find the acceleration. I'm going to show you how to do this two ways. So method 1 is the individual objects approach. In this method, I'm going to write out the F-net equation for each object. So we know the objects are accelerating to the right. That is our positive direction anyway. And also, the forces are balanced for each object in the y direction, so I'm only interested in the x direction here. So if I look at mass 1, the net force acting on mass 1 is m1a, and this is going to equal Fa minus Ft, since Fa is to the right and Ft is in the negative direction to the left. Okay, I can't find the acceleration yet because I have an unknown of tension here. If I look at mass 2, I have only tension in that positive direction. The sum of the forces on mass 2 is m2a, which equals the tension. Now this gives us a relationship for the tension. Ft equals m2a. And I can plug that in here for tension. So plugging 2 into 1. I have m1a equals Fa minus m2a. So m1a plus m2a equals Fa, which gives me A equals Fa over m1 plus m2, and we can solve at this point. So that's going to be 40 newtons divided by 10 kilograms plus 12 kilograms, which is 1.82 meters per second squared. Now, method 2 we can do quite quickly, which is called the system approach. What you're going to do here is look at the entire system as one, and so maybe consider it like this. One object, so all the internal forces, which is tension here, is part of the system. You could also think of it as that tension is equal and opposite, so they effectively cancel. Now we have this one applied force that's accelerating the entire system. So in that case, I have the net force on the entire system equal to m1 plus m2, a, which equals Fa. And we obtain acceleration is the applied force over the total mass. So that gives us the same relationship, but kind of skipping a step, so we go directly to that acceleration. So the benefit of this is that it's quicker, but sometimes it's not as easy to see which forces we need to include, so you can always do individual objects instead. Also, if we then wanted to find the tension in the string, we couldn't do that by looking at the total system because the tension doesn't come into play there. We would have to go to one of these equations to find the tension in the string. Example 23, a 5 kilogram mass sits on a frictionless surface. It is attached by a cable to a suspended 2 kilogram mass by a frictionless massless pulley. What is the acceleration of the masses? All right, let's look at the free body diagram for this system here. We have mass A and mass B connected over this massless frictionless pulley. So this approximation of a massless frictionless pulley means that the tension is the same on either side of the pulley. And it is a good approximation for light pulleys that can spin fairly easily. So we're going to have tension pulling up on mass B and to the right on mass A, and those values will be equal since it's constant in the string. Then I'll have the weight of each mass, FGB, FGA, and a normal force only on mass A because it's the only one that's in contact with a surface. When dealing with connected objects moving in different directions, it can be helpful to use a consistent positive direction. So this is a system, but the masses are actually not moving in the same direction because this mass is not going to go over the pulley. So it's going to move here in the positive direction. So I'm going to use up and around the pulley like this as positive, so that positive is actually down for mass B since that's the direction that the system will accelerate. This will allow us to have the same acceleration for both objects. Otherwise, we would have to worry about doing a two-dimensional problem and comparing the acceleration in each coordinate direction. So this is an easier way to do it. It's like when we used a new coordinate system for an incline, we can do that for connected objects too. Okay, so now let's find the acceleration by looking at the net force on each mass. If I start with mass A here, it's only accelerating in this positive direction. Fn and Fg in the y direction are balanced. So I have the net force on mass A equal to ma times the acceleration, which gives me ma times A equals Ft. So that's our first equation because we have two unknowns here, A and the tension. Okay, then looking at mass B, positive is down since that's the way it's going to accelerate. So the sum of all the forces here will be mb times A, which gives me FGB minus Ft, which is up in the negative direction in this case, equals mb times A, and that's 2. So just like before, I'm going to plug in this expression for the tension into equation 2. So we'll have FGB minus MA times A equals MB times A. So I end up with MA A plus MB A equals FGB. So the acceleration equals the mass of B times G, this force, over these two masses, MA plus MB. So that's 2 kilograms times 9.8 meters per second squared over 5 kilograms plus 2 kilograms, which is 2.8 meters per second squared. And now let's say we did want to find the tension in the string. We're going to go back to one of these equations and solve for the tension. It's already isolated for in equation 1, so that's just one step easier, but we could solve for it in equation 2. So if I do find the tension, I have Ft equals Ma times A. Wasn't asked for this time, but just to show you. So that would be 5 kilograms, which was Ma, times 2.8 newtons per kilogram. I like to just switch the units. Remember, newtons per kilogram and meters per second squared are equivalent. You can write either one, but if I write it like this, you can see that the answer is in newtons. And that gives a tension of 14 newtons. Example 25, if mass 1 has a mass of 10 kilograms and mass 2 has a mass of 7 kilograms, determine the acceleration of the masses and the tension in the rope. This is a really common setup that you'll encounter. It's called Atwood's machine. So it's two masses that are suspended over a pulley. Again, we're approximating it to be massless and frictionless. So let's look at how to find the acceleration. Mass 1 is our heavier mass. We have the weight of it and tension pulling upwards in the rope. Tension on this side, again, it's constant throughout the rope. And then Fg2 on the lighter mass. Let's use the system where we use the positive direction to be the direction of motion. So it's going to move like this. It will slip towards the heavier mass. So mass 1 will move down. That will be the positive direction for mass 1. So that it moves up and around the pulley like this, counterclockwise. So the direction is positive for mass 2. And again, if we do this, we can say A1 equals A2 equals A. So that's why we're using this method. Okay, so let's write out the F-net equation for each mass. For mass 1, sum of all the forces is M1A. So we'll have M1A equals, Fg1 is down. I'm going to write M1G for that force. That's the positive direction here since it's our heavier mass. And then that's minus Ft, which is up. Again, two unknowns, Ft and A, so we'll stop there and look at mass 2. Mass 2 looks similar, but the direction has changed. It's moving up, which will be our positive direction. So I'm going to have the net force, which is M2A, equals Ft, which is up, minus M2G, that's Fg2, which is down. So now I have two equations and two unknowns. So let's rearrange for tension in one and plug it into the other. I'll rearrange for tension here. I'll have Ft equals M2A plus M2G. And now we'll plug this into this first equation, plug 2 into 1. So I have M1A equals M1G minus, and I put this whole expression for tension, M2A plus M2G. Okay, and now we can solve, so I'm going to move this over. We'll have M1A plus M2A equals M1G minus M2G. So solving for the acceleration, I have M1 plus M2, A equals M1 minus M2 times G. So the acceleration is M1 minus M2 times G over M1 plus M2. So that's 10 kilograms minus 7 kilograms times 9.8 over 10 plus 7 kilograms, which gives an acceleration of 1.73 meters per second squared. That's the hard part. Now that we have that, we can find the tension by using the equation where we already isolated for tension. So it's right there. We have Ft equals m2a, which is 7 kilograms times 1.73 meters per second squared plus 7 kilograms times 9.8 meters per second squared, or newtons per kilogram, to give 80.7 newtons for the tension in the string. Now, I've shown one method of solving. You could also use a system approach if you wanted, but then you'd have to look at one mass in order to find the tension. Alternatively, you could have solved for tension in equation 1 and then found it that way. You should get the same result. Okay, let me know if you have any questions on that. For our last example, we'll draw a free body diagram for each box in the system and identify any action-reaction pairs. Okay, so the system looks like this. We have an applied force F acting on a larger box, which pushes into a second box, and then that pushes into a third to accelerate the entire system. So I'll draw each box separately, box 1, box 2, and then box 3 here. So F acts on box 1, I'll add that in. Also, of course, we can go ahead and add Fn on each box and Fg on each box. That's 2 there. Okay, now let's look at the interaction forces. This force pushes block 1, which then pushes block 2. So I need a force here. This is force of block 1 on 2. This must have a reaction pair, so I'm already going to get into labeling those. The reaction pair acts on block 1. It's here. This is F2 on 1. We know that's there because this is impeding the motion of the block 1, having another block in front of it. Now let's look at block 3. It moves forward as well. The reason it moves forward is because block 2 pushes into it. So this is F2 on 3. The reaction of that, of course, is here. The reaction force, which is F3 on 2, since it pushes back on block 2. And that's it. Without friction, these are the only forces, and this would accelerate all 3 boxes together.